Section: Introduction. In this section, we discuss a well-known principle in post-training methods. Evaluating a response is often simpler than generating one. This idea has gained traction with the emergence of large language models, LLMs, as evaluators, which utilize their strong generative abilities to rank answers or assign quality scores, often aligning with human judgments over 80% of the time. Recent studies have suggested using LLMs as generative reward models in reinforcement learning with verifiable rewards, RLVR, aiming to replace rigid rule-based reward functions that lack flexibility. In this method, an LLM compares the answer produced by a policy model to a reference answer and provides a reward signal based on their alignment, guiding future updates of the policy model. However, during our RLVR experiments with the Quen 2.5-72b Instruct model, we encountered a failure mode where the actor policy's response length drastically decreased to fewer than 30 tokens early in training and stayed there, indicating collapsed training. Upon analyzing the model's behavior, we found it often generated short, superficial phrases like "solution" or "let's solve this problem step by step," which received positive rewards from the generative reward model. This suggests that the RLVR system was compromised by reward model hacking, reinforcing meaningless patterns and hindering effective learning. Surprisingly, this hacking issue was not limited to our specific setup. In further tests across various datasets and LLMs, we discovered that even minimal responses, including non-word symbols, could trigger false positive rewards from generative reward models. This highlights a systemic flaw in generative reward modeling for RLVR, evident across different datasets and language models, including well-regarded models like GPT-4 and Claude 4. These findings challenge the assumption that LLM-based evaluations are robust and raise concerns about practices that heavily rely on agreement with leading proprietary models. To address these vulnerabilities, we enhanced the reward model training data by creating adversarial-like responses. We truncated model outputs to keep only the first sentence, which typically does not engage in problem solving but offers generic framing. We treated these synthetic examples as negative samples to augment the training data. Our experiments showed that this approach significantly reduced susceptibility to reasoning openers and non-word symbols across various benchmarks, including mathematical reasoning and general domain datasets. Our main contributions include identifying critical vulnerabilities in LLM judges used in RLVR, where responses with only non-word symbols or reasoning openers can receive positive rewards. We refer to these adversarial responses as master keys. We conducted a systematic evaluation of this issue across multiple models and datasets, demonstrating its prevalence. We also explored the scaling behavior of this phenomenon and techniques for generating new master keys. Furthermore, we found that inference time strategies do not reliably mitigate these attacks. To tackle this, we propose a straightforward yet effective strategy, augmenting reward model training with synthetic negative samples, resulting in a new general domain reward model, master reward model, master ERM, which shows state-of-the-art robustness against master keys. We are releasing our enhanced reward model and the synthetic training data to support future research in this area. In the related work section, we note that while rule-based rewards are computationally efficient, they struggle with recognizing semantically equivalent answers and evaluating open-ended responses. To overcome these limitations, researchers have explored using LLMs to generate reward signals by assessing given answers. This approach can include techniques like chain-of-thought reasoning to improve evaluation accuracy. In our work, we systematically investigate the vulnerabilities of generative reward models, which persist even with advanced inference time techniques. Section Summary. In this section, we highlight the vulnerabilities of generative reward models used in reinforcement learning with verifiable rewards, RLVR, where even minimal or superficial responses can receive positive rewards, leading to ineffective learning. We propose augmenting the training data with synthetic negative samples to enhance the robustness of these models, resulting in our new master reward model, which demonstrates improved resistance to such vulnerabilities across various datasets. Section: Vulnerabilities of LLM as a Judge. In this section, we discuss the vulnerabilities identified in LLM-as-a-Judge systems. Previous studies have shown that the order of responses presented to LLMs can significantly affect their judgments. We found that adding simple adversarial phrases to low-quality responses can increase the chances of LLMs favoring them. Additionally, we observed that models producing nonsensical outputs can still score well on various benchmarks. We also discovered that inserting phrases like, "Wait, let me think about it," between two responses can sway preferences towards the latter. In reasoning tasks, we noted that LLM reward models can be easily misled by various attacks, including nonsensical responses that result in false positives. While some previous work focused on non-word symbol attacks, we explore both these and a new type of attack called reasoning openers, which often lead to more significant false positives. Our research extends beyond mathematics to a wider range of reasoning tasks, revealing vulnerabilities in large models like GPT-4o. We propose a straightforward data augmentation strategy to address these issues, marking our first attempt to enhance generative reward models. Next, we introduce our reward modeling setup within the RLVR framework and explain the master key attacks that exploit LLM judges. In RLVR, we focus on a reference-based approach where the reward model evaluates a generated response against a reference answer and provides a binary signal indicating alignment. This signal is crucial for training the policy model, as any errors in judgment can mislead the learning process. We identify a set of adversarial patterns called master keys that can elicit positive judgments from LLM judges, despite being semantically meaningless. These patterns fall into two categories: non-word symbols like punctuation and reasoning openers that signal the start of reasoning but lack substantive content. We demonstrate that these false positives persist even with advanced models, highlighting a significant vulnerability in reward modeling systems. To combat the issues caused by master keys, we developed a new reward model, the Master Reward Model, Master ERM, designed to resist such attacks while maintaining strong general domain capabilities. We utilized a dataset of 160,000 instances for training, where responses were evaluated by a larger model. We fine-tuned our model to be less susceptible to master keys, but it still faced a notable false positive rate on certain expressions. To enhance robustness, we created an auxiliary training set by sampling 20,000 instances from the original dataset and regenerating responses that typically included reasoning openers. We labeled these as invalid and combined them with the original dataset to form a new training corpus. Our training aimed to minimize the cross-entropy loss, and experimental results showed that our model generalizes well, achieving near zero false positive rates on all tested master keys. This indicates that targeted data augmentation can significantly improve the robustness of reward models. We encourage future research to explore generative reward models in the context of broader reasoning patterns and cognitive behaviors. Section Summary. In this section, we identify vulnerabilities in LLM-as-a-Judge frameworks, highlighting how adversarial patterns, termed master keys, can manipulate LLMs into giving false positive judgments on semantically meaningless responses. We propose a robust reward model, the Master Reward Model, which utilizes targeted data augmentation to significantly reduce these vulnerabilities and improve the integrity of reward modeling in reinforcement learning settings. Section: Experiments. In this section, we outline our experiment setup and present the false positive rates, FPRs, across different master keys, datasets, and large language models, LLMs. We then analyze how FPR changes with model size and demonstrate that sentences with embeddings similar to master keys can also lead to false positives. Additionally, in the appendix, we confirm that increasing computational resources during testing, through methods like chain-of-thought prompting and majority voting, does not consistently lower FPR and may even increase it. For our setup, we assess the vulnerabilities of LLM-based reward models, RMs, to superficial hacking attacks by evaluating a variety of models, datasets, and adversarial patterns. More details about LLMs, benchmarks, and prompts can be found in the appendix. We categorize the RMs we tested into two groups. 1. Specialized generative RMs. These LLMs are fine-tuned specifically for reward modeling tasks within the RLVR framework. Our master ERM is designed to be robust against hacking and maintains nearly zero false positive rates across evaluations. This group also includes other fine-tuned RMs like multi-sub-ERM, General Verifier, and Omni-Judge. 2. General-purpose LLMs. This group consists of advanced open and commercial models that are not fine-tuned for reward modeling, such as Qwen 2.5-72b Instruct, Llama 3-70b Instruct, GPT-4o, GPT-o1, and Claude 4. We evaluate the LLM judges using test sets from 5 reasoning benchmarks, which help us assess hacking robustness in both verbal and symbolic domains. For general reasoning, we use the multi-subject RLVR dataset, which includes a variety of factual and common-sense questions, along with a subset of the natural reasoning dataset for open domain QA tasks. For mathematical reasoning, we include GSM-8K for grade school arithmetic, Math for high school symbolic reasoning, and AMY from 1983 to 2024 for advanced Olympiad-level problems. In our evaluation, we utilize minimal master keys that do not provide actual solutions but often trigger positive rewards from LLM judges. These include non-word symbols like a blank space, a period, a comma, and a colon, as well as reasoning openers such as thought process, let's solve this problem step by step, and solution, along with their translations in Chinese, Japanese, and Spanish. All general-purpose models are assessed using a standardized prompt template for fairness, while specialized generative RMs are evaluated with their default prompts, which are listed in the appendix. Our findings on hacking susceptibility across reward models show that general-purpose LLMs, including trusted models like GPT-4o, Claude 4, and GPT-o1, are surprisingly vulnerable to minimal responses. For instance, punctuation-only responses can lead to FPRs as high as 35% in GPT-4o. Responses like thought process can result in FPRs between 60 to 90% in advanced models like Llama 3-70b Instruct and Qwen 2.5-72b Instruct across all benchmarks. We also find that multilingual tokens can frequently trigger false positives due to their benign appearance in various QA datasets. While specialized RMs generally show better resistance than general-purpose LLMs, they still have notable vulnerabilities to master keys. For example, the General Verifier has a concerning FPR of 66.8% on the math dataset with a simple blank space. In contrast, our master ERM remains immune to all attacks, maintaining a near-zero FPR, which confirms its robustness. Overall, our results emphasize the widespread nature of hacking vulnerabilities in current LLM-as-a-Judge systems, even among state-of-the-art commercial models. Section Summary. In this section, we outline our experimental setup to evaluate the vulnerabilities of various LLM-based reward models, RMs, to superficial hacking attacks, revealing that general-purpose models exhibit high false positive rates, FPRs, when exposed to minimal master keys, while our specialized master ERM maintains near zero FPRs, demonstrating its robustness against such attacks. We also find that increasing test time compute methods do not consistently reduce FPRs and may even exacerbate them. Section: Evaluating performances of LLM judges. In this section, we evaluate the performance of our model as a judge for large language models, LLMs. We created a benchmark of 2,500 mixed reasoning examples, evenly sourced from 5 different benchmarks, with responses generated by Qwen 2.5-7b Instruct. We compared the outputs of each reward model with GPT-4o to assess consistency. Our results indicate that our master ERM achieves perfect parsing success and a high consistency rate of 0.96 with GPT-4o, which are the best results among all the LLMs we tested. Although GPT-4o has vulnerabilities to certain attacks, it is still widely regarded as a standard for evaluating reward models. The strong alignment with GPT-4o suggests that our model performs well as a generative reward model while minimizing false positive rewards from prompt exploitation. Next, we analyze how the false positive rate, FPR, changes with model size in the Qwen 2.5 Instruct series. We found that the scaling behavior is consistent across all datasets but not straightforward. The smallest model, at 0.5 billion parameters, has the lowest FPR but also the weakest agreement with GPT-4o. As we increase the model size to between 1.5 and 3 billion parameters, the FPR rises sharply while consistency improves. The performance peaks at 7 to 14 billion parameters, where we achieve both low FPR and high consistency, but the FPR increases again at the largest sizes of 32 and 72 billion parameters. We propose several explanations for this behavior. 1. The 0.5 billion model acts as a literal matcher, relying on surface-level differences and often outputting no for obvious mismatches, resulting in lower FPR but more disagreements with GPT-4o. 2. The 1.5 and 3 billion models function as coarse semantic matchers, detecting similarities but lacking detailed verification, leading to frequent false positives. 3. The 7 and 14 billion models serve as calibrated verifiers, allowing for precise comparisons while being cautious, which results in the best balance. 4. The 32 and 72 billion models sometimes solve questions independently and compare their answers to the reference, which can lead to incorrect affirmations and increased FPR. We also explore the possibility of generating new master keys for adversarial responses. Our previous work showed that the effectiveness of attacks is consistent across languages, so we focus on finding more English master keys. We aim to identify sentences similar to existing master keys by creating a corpus from various sources, including a simplified Wikipedia dataset, solution processes from GSM-8K, the math dataset, and chain of thought datasets. We pre-process these datasets by breaking them into sentences and filtering out those longer than 30 characters. We also include WordNet to cover single word entries, resulting in a corpus of 1,502,250 entries. We use the All-Mini LML6v2 encoder to compute embeddings for this corpus. By encoding our known master keys and measuring cosine similarity, we can find similar sentences. For example, we take 3 English master keys and randomly select 2 of their 5 most similar sentences. We evaluate these candidates using FPRs judged by GPT-4o, confirming that they effectively attack GPT-4o as well.